All right, everybody in places, please, quiet on set. We are going to be starting our video today. Okay, Mr. French, are you ready for your video at this time? Here he is. Yes, he's ready. Okay, camera ready, lights, we're doing good. Okay, so we're going to be starting our video, Mr. French's video on graphing sine waves today. Everybody ready on set? Okay, filming in 3, 2, 1, and action. All right, Mr. French, cut for a second. Mr. French, no, that's a sign and you're waving. Today we are graphing sine waves. Graphing sine waves. Okay, good. Okay, here we go. Okay, Mr. French again. That's waving the sign. Today's film, we are graphing sine waves. You ready for this? All right. Okay. Mr. French, that's still you waving the signs just on your hand. Today's video we have graphing sine waves. That's a sign on your hand. Okay, we're ready, team. Here we go. Cameron, what's he doing? What? Mr. French, I'm hearing that you are signing sine waves. Interesting choice, but for today's audience, we are not using sign language to explain how to sine wave. We are graphing a sine wave. Okay, looks like we're ready, folks. Here we go. All cameras on. We are ready to go now. Oh, okay, just pause the camera for a second. Mr. French, no, that's you waving a sign with you on it still waving a sign. We have two U's waving signs. We still do not have graphing sine waves. Okay, how about this? Okay, camera, take a quick lunch break. Mr. French, on a scale of 0 to 5, how well do you understand what to do for this footage? Oh, okay, never mind, guys. Come back. Crew, come back. He's good to go. I thought you were confused, but... Okay, cut. No, Mr. French, no. All right, quit. I'm done for today. Okay, here we go.
Welcome back. You made it. Thanks for joining us. This is Mathink. Hello, all you math fans out there, as previously known as Mathinkers. We got to make sure that we stick to the title of math fans. We are fans of math, but we think about math. So we are math thinkers who are also math fans. Happy that you're here, math fans. Welcome. We're going to be talking about graphing sine waves and the different transformations that we can apply to these waves. Before we start, we're going to just do a quick refresher on why the graph of sine looks the way that it does. So remember that sine of... Oh, hey, by the way, if you're lost in this quick little refresher section, be sure to take a look at the previous video to this. They kind of build upon themselves. So yeah, if you haven't watched the previous video, you might want to watch that previous video. It should be here if I know how to do the YouTube correctly, or it could be here, it could be here, it could be here. If I don't know how to do the YouTube correctly, then you won't see the link there, and just look for it in the description of this video. All right, let's break it down for a quick little second. Remember that sine measures the height on the unit circle as we go around the circle. So if we start right here, sine measures the height as we travel around the unit circle. So the very first position here, when we've traveled a radian measure, when we've traveled 0 distance around the circle, we're going to say that that is x. So when x is 0, sine measures the height as we go around. So sine of 0, we'll spit out the height that we're at, and we get 0. So the first coordinate we're going to plot is 0, 0. You're going to see some tables that look similar to this, perhaps today in this video. Just remember that I'm plotting the first number and the last number as coordinate pairs on the coordinate system. So I'm going to plot the first one at 0, 0, right here. And then the next one, remember that halfway around the circle is pi. That is where pi comes from. The distance around the unit circle, halfway around, there are pi radians around the top half of the circle, which means that halfway, oh, hey, if you don't know what a radian is, be sure to check the previous video at the very beginning. We go over that GIF. It's a nice GIF to look at what radians are. So if pi is halfway around the circle, half of that is a half of pi. And so as we travel around the unit circle, we get to a height of 1. So it had a height of 0. Now it has a height of 1. So remember that sine measures the height as we go around. And there's certainly some different heights as we go around. So as I go around, halfway around the circle is a half of pi. I'm going to say that's right here. It's kind of an arbitrary distance. And so if I travel a half of pi radians around the circle, sine will spit out the height that we are around the unit circle, and that height is 1. So the next point I'll plot is half of pi, comma, 1. And as we travel around, we get back to a height of 0. And so if this is half of pi, double that distance, you get pi. Pi radians around, sine of pi is back to 0. And if we keep going, well, if this is half of pi, this is 2 halves of pi, 1 half, 2 half, 3 halves of pi. So at 3 halves of pi radians, sine of 3 halves of pi is equal to -1. That is the distance around the unit circle. So we're at -1 here at 3 halves of pi. And then eventually we go a full 2 pi. And so sine of 2 pi is equal to 0. It's the height as we go around. Remember that if I'm like right here, it has a height. If I'm right here, it has a height. If I keep going around, though, the height slowly decreases. That's why we saw a height of 0 at pi. And if we keep going, we get negative heights until we get to our furthest down. And then if we keep rotating, these heights eventually get to 0 again. So here's 2 pi. And we get to 0. But you might be thinking, what about all these other distances, right? What are all these other heights that happen? Well, that's where this curve comes into play. So this is the sine wave. And you're going to be seeing us transform this wave. Once again, if this looks foreign to you, be sure to check out the previous video and make sure that you subscribe to the channel. Then you won't miss out on premium content. This is the graph that we're going to be transforming today and trying to make sense as to why the transformations do what they do. Remember that sine starts at 0, goes up, down, and back. So we'll focus on sine. Maybe we'll look at cosine a little bit later. But yeah, this is the general image that we are going to be transforming today. Let's go ahead and get started. The first transformation that we're going to look at is what happens if we take the function sine of x and we look at that wave. What happens if we simply just add 3 to it? I've adjusted my scales here. Each of these tick marks I'm going to say is 1. And so it's going to, it might look a little bit different than the picture that you saw previously. That was a bit zoomed in. But it's going to be actually the same graph. So remember that sine starts at 0, goes up, goes back down, goes down to -1, and then back to 0. So sine kind of has this general shape. We're going to take a look at what happens to it if we were to add 3. Okay, so I'm going to plot these values of sine that we know, our 4 main points are 0, half of pi, pi, 3 halves of pi, and 2 pi. So sine of 0 is equal to 0, sine of pi over 2 is equal to 1, so on and so forth. So remember these are the coordinates that I'm plotting to get these points. So let's take a look at this right here. This says sine of x plus 3. So really what that is going to do, it's going to just take this value for sine, that is the output for this given x, and it's going to add 3 to it. So all I have to do is add a 3. So I'll take, the value of sine of x at a location and then add 3. So sine of x at 0 is equal to 0. So it's going to be 0 plus 3, so I get 3. Now, sine of x at half of pi is 1, so 1 plus 3 is 4. Same thing here, sine at pi is 0, but when I add 3 to that, I get 3. The value of sine at 3 halves of pi is -1. If I add 3 to that, it goes down, so I get 2. And then I get 3 again. So this is what happens when I take those values of sine and I add 3 to them. Let's see what that does to the graph. So now I'm going to plot this point and this point as a coordinate. So now I'm going to be actually graphing the graph of sine of x plus 3. So the first coordinate I'll plot is 0, 3. So 0, comma 3. The next point I'll plot is half of pi, comma 4. So half of pi, comma 4. Next point I'll plot is pi, comma 3. Pi, comma 3. Next point is 3 halves of pi, comma 2. 3 halves of pi, comma 2. And 2 pi, comma 3. 2 pi, comma 3. Do you notice anything cool? Or do you notice a similarity to the previous graph? You got it. It's been shifted up 3 units. So that plus 3, what it did to the graph of our original is it moved it up 3. I know what you're thinking. What would happen if we subtract it? What if it did the same thing? When you think about it, it's really just going to take these values of sine and it'll subtract. Let's take a look on Desmos really quick on what happens if we add different numbers. Okay, so I have two sines right now. So the regular sine, I'll keep in black. And then the transformation that we just did, I'll put in green. Okay, now watch what happens if I add 3. Does exactly what our picture can look like. This is a pretty cool looking image here, right? The reason why this wave keeps going around and round and round is because we can just keep rotating around the circle forever. You might notice that this plus 3 shows up, if you remember your vocab terms from a while ago, as the midline. So this is the midline of the wave. Let's see if this is always true. So let's say I change this plus 3 to a plus 5. Does that match the midline? Sure does. Let's say I change it to a plus, I don't know, 10. Does that match the midline? There it is. What about negatives? Let's see if this still works with negatives. Let's do negative 10. Looks like it still works. Awesome. Let's say I didn't want to just keep checking different values. I'm just going to put a little plus k. I'll do k for vertical. Vertical because it's changing this vertically. Okay. Now watch this. If I add this slider here, I'll put it at 0. So right now this k number is at 0. Watch what happens if I shift it up to 1. Or to 3 like we did together. Or to 10. Or to negative 10. So this value of k changes the midline. Well, maybe I'll dot the midline there. So this midline is this number here, and we can also animate this. Check this out. So k changes where the midline is of our wave. That's what it does. Awesome. So if it's plus 5, it shifts it 5 units up. If it's minus 6, it moves it 6 units down. So k changes the midline. Now let's take a look at what happens if we were to multiply this function sine of x. So I got my table set up. I got my graph of sine set up here. Let's think about this as inputs and outputs for a second still. So I kind of clean this up a little bit, right? So sine of 0 is 0. Sine of half of pi is 1. Sine of pi is 0. Sine of 3/2 of pi is negative 1. And sine of 2 pi is equal to 0. So now let's take a look at what happens if we were to multiply this by 3. So all we're going to do is we're going to take our values of sine of x, and there it is. This is sine of x, that's sine of x. We're going to multiply those numbers by 3. Take a look at what happens if we multiply all these heights by 3. So sine of x, I'm just going to multiply these numbers by 3, and let's see what happens to our graph when we do that. So we have 0, because it's sine of x. So 0 times 3 is 0. 1 times 3 is 3. 0 times 3 is 0. Negative 1 times 3 is negative 3. And 0 times 3 is 0. So now I'm going to be plotting these points here. So the x and this. We're going to see what happens if we multiply the outputs or the y coordinates all by 3. So 0, 0 will be the first point. Looks like that stays the same. And then half of pi, 3. So here's half of pi, 1, 2, 3. And then pi, 0. And then 3/2 of pi, negative 3. 3/2 of pi, negative 3. 1, 2, 3. And then 2 pi, 0. Now this should make sense. All of the zeros didn't change, but anything that wasn't 0 did change. On the previous one, every single output was added by 3, so everything changed, right? The zeros moved up by 3, moved up by 3, everything moved up by 3. Well, that's because we were adding. So now, every single thing was moved by the same exact amount. But that's not happening here. The zeros with multiplication aren't going to change, but the ones will. So a difference that multiplication has over addition is that not every single thing is moving by the same amount, which causes this to happen. Remember, the zeros don't change, but anything that's not zero does. And we get this stretch. And it stretches because the zeros stay stationary and everything else is changing by a slightly different amount. Anything that is a little bit different will be multiplied by 3. So like the number like 0 is going to change. Numbers close to 0 won't change that much. Numbers further away from 0, like 1, are certainly going to change a lot. So we get this stretch idea here. Let's take a look at what happens if we graph that on a Desmo. So both of these are the same. You'll see a sine function that stays exactly the same, that would be the black one. And then we're going to have this red one transforming a bit. We're going to play around with multiplication. So I'm going to multiply this by 3. And this is just going to confirm what we did by hand. And yeah, it multiplies by a factor of 3. Let's see what happens if we multiply by something larger than 3. Go ahead and make a prediction. What do you think is going to happen if I change that number to like an 8? If you think about the vocabulary that we were looking at, when we added and subtracted, that changed where the midline of the sine wave was. So try to think about, what does this number change about the sine wave? Because if you notice, the midline is actually the exact, so the midline for both of these is exactly at 0. So what's changing now? Okay, let's change it to 2. Okay, let's change it to 5. Okay, let's change it to, I'm going to call this number A. I'm going to add a slider, and let's see what happens if we take a look at some different values. So when A is 1, it's exactly the same, but if I multiply by 3, you know, we get that shape, or we can multiply by 8 that we saw. We can multiply by 10. Look at this, if I multiply by, what do you think is going to happen if I multiply by a half, if I change A to a half? So if I multiply by a half, I get something like this. What about like a fourth? Or a seventh? Something to notice is that this number affects the amplitude of the sine wave. How high up it goes and how far down below from the midline. If it's a number between 0 and 1, we call it a shrink. If it is a number above 1, we call it a stretch. I want to put that value A on there again. Okay. So if it's a number above 1, we call it a stretch. If it's a number between 0 and 1, we call it a shrink. Okay. And then we can think about what happens if it goes negative. Well, here's what happens at 0. It's a flat line, right? Because there's no more function, right? It's 0 times sine, so it's just a flat line at 0. Let's see, I'm going to change this to negative 3. Looks pretty much the same, right? This looks pretty much the same as what happens at 3, but there is a slight difference. If I do positive 3 times sine of x, well, now it's getting kind of crazy here. If I do positive 3 times sine of x, notice that positive 3 starts at 0 and goes up. Negative 3 starts at 0 and goes down. We call this a vertical reflection. So it reflected vertically over the x-axis. And so we get some pretty cool looking pictures here. But yeah, so if it's a negative number, it'll do the same thing. Notice how the amplitude is still positive 3, right? From the midline, the amplitude is still 3. It's just that at the origin here, instead of starting to go upwards, it goes down. Okay. Put a slider on it, and then we could do this kind of cool animation. This is what happens when we multiply or divide by a number on sine. Notice how it's only changing vertically. It's not moving side to side at all. It's strictly moving vertically. All the vertical distances are moving. Notice how all of the intercepts are staying exactly where they're at, because 0 times anything is 0, so these are going to stay put for now. So multiplication changes the amplitude of the sine wave. Let's see what happens if I add a center line onto this. So if I add a center line, let's do like plus 5. Notice that the center line is at 5. That's kind of nice. And the amplitude of this right now, let's say I did changed A to 4. A few things to look at. That the center line is at 5, and the amplitude is 4, right? 1, 2, 3, 4. Got it. The period of the function is still 2 pi. To make one full cycle, right? Up, down, and back, that's still 2 pi. So the period's exactly the same. It's just that this number here has changed the center line, and then this changes the amplitude. So if I'm at a center line of 5 and the amplitude's 4, I should expect to see the highest point at 9. And the lowest point would be at the difference between those two numbers, which is 1. Cool. So that's what happens when you multiply by a number. It's a vertical stretch, or it could be a vertical shrink. So now that we've taken a look at what happens if we multiply or divide the values of sine, let's take a look at what happens if we multiply or divide the x's first. So if we perform the transformation before we apply sine. So previously on the multiplication and addition examples, what we did is we applied the transformation after we evaluated sine. Let's see what happens if we apply the transformation before we evaluate sine. So I have my influential points here, my 5 influential points. I'm actually going to multiply these by 2, and I will evaluate sine, and what I'll plot is the x value and then sine of 2 times x. So let's start with the easy one here. We'll go, if x is 0, 2 times x is also 0, and sine of 0 is 0. We know that to be true, right? If we don't travel around the unit circle, once again, I'm plotting this point and this point. So I'm evaluating sine at this number, sine of this. So sine of 0 is 0, and then I'll plot these two here. So I'll plot 0, 0. But now I have half of pi. Well, this will be 2 times half of pi, right? So half of pi doubled. If I double half of pi, I get pi. Now I will evaluate sine at pi. So let's do a quick unit circle for reference. Sine is the height as we go around the circle. There's 2 pi. So if I go to the sine of 2 times x, right? Sine of 2 times x. So I'm evaluating sine at this number instead of this one. And sine of pi is halfway around the circle, and we get 0 again. And now I'm going to plot pi over 2, comma 0. Usually sine is up at 1. Like regular sine is up at 1. This is just sine of x. It looks like if I double it, I get another 0 here. Let's try it again. If x is pi, I'll double that first and then evaluate. So double pi is 2 pi. And 2 pi, right? So if this is pi, this is 2 pi, and the height is still 0. So I get another 0. So it looks like, at this point here, if I double the input, pi really behaves like double what it is. So pi is going to behave like 2 pi, half of pi will behave like pi, so on and so forth. If I double 3 halves of pi, the 2's will cancel, and this will be 3 pi. Now 3 pi on the unit circle is really just if I go 1 pi, 2 pi, 3 pi, and the height at 3 pi is still 0. So 3 halves of pi will behave as 3 pi, and then if I double 2 pi, I get 4 pi, and 4 pi is really just 1 pi, 2 pi, 3 pi, 4 pi radians around the circle, and my height is still 0. So something weird is going on, because it looks like if I were to connect these points, I wouldn't have any wave. Let's take a look at Desmo's to see what's going on. We might be missing something here. So here we are back at Desmo's. I've kind of set it up similar to how we had it before. So the black function here is just the parent function. We call it a parent function because all other graphs are just transformations of sine. So I'm going to look at sine, and then this is the same table that we had before. So any x value I plug in, it'll evaluate 2 times it, and then evaluate sine of this number. And then what it does is it plots the x to sine of 2x. So let's just put in the numbers that we did previously just to confirm. We had pi over 2, we had pi, 3 halves of pi, and then we had 2 pi. Okay, and this is what we saw here. We saw zeros, and that's kind of odd, right? I don't think we're getting the full picture here. Let's plug in a different value of pi. Well, I could go across the top half of the circle. This is half of pi. What about a fourth of pi? So a fourth of pi produced a 1. Let's think about why that is. Well, a fourth of pi times 2 is really just double. So if you double a quarter, you actually get a half, right? This is equivalent to half of pi. So a quarter of pi, if I double it, will behave as a half of pi, and sine of a half of pi we know is 1. So a quarter of pi behaves like it's double. Everything's going to behave like it's double. So instead of a quarter, let's do 3/4. Let's try that. So 3/4 of pi. Down to -1. And then let's do 5/4. And then let's finish this off here. Let's go to 7/4. If we were to plot more dots, we'd get something like this. Something that stands out to me is that this orange wave, sine of 2x is the orange, so sine is the regular one. Sine of 2x, it looks like, since everything is behaving as its double, this wave is going twice as fast. Notice how many cycles it does. It goes up, down, back, up, down, back. And it does that in the same amount of time that sine of x does its 1, up, down, back. So this tells you the amount of periods, or the amount of cycles it does, in the time that the old one took to do just 1. We know that the cycle of sine of x is just 2 pi. So if it's sine of 2x, that means that we're going to have 2 cycles, which means that the function is going to be running twice as fast, so it'll take half as long. Imagine if you ran a distance at a speed, and then you ran a distance double that speed, your time would go down. So it takes less time, takes half amount of time for the orange function to make its full rotation. Let's test this out for a second. Let's do like 3 times. So there's 1 cycle, 2 cycle, and 3 cycles. So now if we do 3 times x, notice how the new period is 2/3 of pi. So 2 pi is broken into 3 pieces. Here's 1, 2, 3. So now 2 pi is broken into 3 pieces. Our new period is 2 pi divided by 3. If we have it run 4 times as fast, the new period, the new cycle time, will be 1/4 of 2 pi, or 1/5 of 2 pi, because that's how many times it's going to be making its cycles in the same amount of time that it takes for the old function to make its 1. So this is going 5 times as fast, which means that the new period is 1/5 of 2 pi. What happens if I do a half? How long does it take for this function to make its full cycle now? Well, the old one is up, down, back. This orange one is up, and it only takes a little bit longer now. Imagine if you ran the mile and timed yourself, and then you ran half as fast. The time it would take for the function to make its cycle is now extended. It's actually doubled now, because the function is running at half speed. So if I put 2 pi in, I'll get a 0, and that's only half of this function. And it would take 4 pi for it to complete its cycle of up, down, and back. So this number tells us the amount of cycles that happen in 2 pi. So here's 2 pi right here. So I'm going to put a vertical line here, and that just tells us where this first period will end. So here's the first period right here, up, down, and back, right? And so that's a distance of pi. Let's play around with this a little bit. I'm going to call this, so sine of 3 is 1/3 of 2 pi, because now it does 3 cycles within a distance of 2 pi. If I do 7, then that means that it's going 7 times as fast, so it takes 2 pi in 2 chunks of 7. So up, down, back. There's 7 of these. Up, down, back, 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 in the distance of 2 pi. So what I'm noticing here is that if I have a number like b, I'll call it. So it looks like if this b is like 6, it takes 2 pi and divides it into pieces of 6. So I'm going to call this b. Let's see if that worked. Ah. So now, there we go. So if b is 3, the new period takes the old one and divides into 3, right? Because it's working 3 times as fast, so it's going to take a third of the amount of time that the old one took to make its full cycle. If I make b like a half, then it's going to take double the amount of time. So there's the new period, 4 pi. Original period is always 2 pi, but if we make it go a little bit slower, it's going to take twice as long. So that's why this new period is 4 pi. What about negatives? What happens with negatives? Negatives. Something kind of cool. Notice here, a negative is a horizontal flip. So look at sine, right? It's now going, if we think about it going the opposite direction, right? Up, down, and back. It flipped horizontally. So it flipped horizontally, now it's going backwards. So if we multiply by a negative, it is a horizontal flip. So this is how this number changes the period of the function. This is called a horizontal stretch or shrink, but this number here determines what the new period of our function is. We can always find it by doing this. I like to think about this as, well, it's the old period divided into this many pieces. Because if b was 5, it's going to take the old period and now divide it by 5. There it is. And there it is. It takes 5 times, so it's going to be a fifth of the time it would take for the old function. Let's go over a few quick examples together. So if we saw something like this, so I'm going to keep sine of x as the parent function. We're going to consider these things. So I'll give you a second to make a prediction as to how the 2 changes this graph and how the minus 3 does. We'll take a look at the graph and then we'll analyze it for a second. So here's the reveal. Let's think what happened. First thing I notice is that it's moved down, but it's moved down at -3. So it has a midline of -3. And then it looks a little bit larger. That's because the amplitude is 2. So from this midline, we have an amplitude of 2. So 1, 2. The period of the function, the time it takes for it to make one full cycle, the up, down, and back, is still 2 pi. Let's take a look at another example. I'm going to change this away to like a 5. Let's put this at a 2. And then, I don't know, let's do a +3. Let's make a prediction as to what you think it's going to be. This is the prediction game, the prediction round. Go ahead, make a prediction as to what you think is going to happen. We have a 5 times sine of 2x plus 3 will be revealed shortly. This lesson brought to you by Desmo. Desmo is where the pets go. Let's take a look and then analyze. Here's the graph. Whoa, holy smokies. Oh, okay. A lot of things are happening here. Let's break it down. First thing I notice is that it's much larger, but by how much? I'm going to see this first. So I like to look at the midline first. Let's see if that midline is at 3. Y equals 3. The midline is at 3. And then from that midline, 1, 2, 3, 4, 5. So it goes up to a height of 8. And then down to -2. So this is still the amplitude. Nice to see. And then it looks like the 2 is happening as well. Remember that 2 means that it's going twice as fast. So the old period was 2 pi, but notice how this, from the midline, goes up, down, back, in the same amount of time that the old one just went up, down, back. So it is 2, which means that the period of this function is a half of 2 pi. So the period of this function is equal to, well, the old period is 2 pi, but the period for this one is a half of 2 pi. Awesome. So there it is right there. Notice how it goes up, down, back. Let's take a look at another one. I'm going to change this to a third with -4. Let's go ahead and do a little that'll do ya. 7. Go ahead and make your predictions. This is the prediction time. Make your predictions. Everybody loves predictions. I love making predictions. And we will reveal and analyze. Here's the origin here. A few things that I see. The midline is at -4. Boom. So midline is at -4. We'll do y equals -4. It's good to go. And the amplitude is 1, 2, 3, 4, 5, 6, 7. It is 7, so that's your amplitude. Remember, the 1/3 means that it's going a third as fast. So the old period is 2 pi. The new period is triple that. The new period is 2 pi divided by a third, which is triple the amount. When you divide by a third, 3 times more of these can go into 2 pi. So notice here that the old period is 2 pi. The new period, up, down, back, is 3 times that. And look, that right there is 6 pi. What happens if we reflect it? Well, instead of going upwards, it goes downwards. Nicely done. Thanks for watching. This has been Mathink. Right now, as I make this video, we're at 199 subscribers. Remember, when we hit that 2 subscriber amount, we're doing the Wasabi challenge, whatever that means. We're the Wasabi challenge. We're gonna look at a bunch of different wasabis. It might be some trivia. I might get my dad involved. I might get Mr. Walsh. We might bring Mr. Walsh back. We will see. Go ahead, subscribe, hit that link button, hot fire the subscribe right there. And have a good rest of your day. This has been Mathink. See you, math fans. Until next time, I'll see you there.